284C3M1B7C8E13C9C6D3p38d19d7b43. Line 22f1fa19c3m1b7c8e13c9c6d3p38d19d7b43. Telecom Wavelength Semiconductor signals, 5G Wow Seti. There's the alien radio signal, and here's the data. Okay, so this is talking about the pump wavelength Chalcogenide fibers, semiconductor. I spelled fibers wrong. Semiconductor PDF file results for UFO space signals from the WOW data. This is continuing from a very long PDF file. So data is going to continue from the previous video, May the 4th, 2013. I worked on this particular data. Today's May 20th. It started at line 37, the very last number, and we're up to 43 now. So mid-infrared optical frequency combs. Then you want to see CW, mid-infrared OPO pump laser. You want to watch each video because each video is a little different part of the PDF file, PDF results. And it's really interesting. It's talking about combs and lasers and diffraction and all sorts of cool stuff. Then it talks about high power comb line, and then the phase noise infrared signals, then the infrared comb nodes frequency signals, and the last one was frequency comb spectrum signals. The keywords were formula particles, wavelength formulas, and Compton wavelengths. And I brought up formula units, tile, mole, and 1472. And I Googled it and got all this information. Yes, you can see my typing isn't the greatest, especially first thing in the morning. Okay, so mid-infrared optical frequency combs at 2.5 ohm based on crystalline microresonators. Figure 1a, the magnitude of D2 is monotonically increasing with wavelength above 1.55 ohm in MGF2 resonators, anomalous dispersion. So this was the original PDF, and these are all the scientists that worked on it. From Nature Communications, it was January 2013. As shown in the simulation, figure 1a, the magnitude of D2 is monotonically increasing with wavelength above 1.55 ohm in MGF2 resonators, anomalous dispersion. Consequently, intrinsically low phase noise Kerr combs can be expected across the entire mid-infrared region. This is in contrast to the telecom wavelength region around 1.5 ohm, where we could not observe intrinsically low noise states in the same resonators despite various pumping conditions. In agreement with the understanding of phase noise in reference 30. In the present work, the choice of pump wavelength equals 2.45 ohm originates from the current limitation of the available OSA and the coupling fibers strongly increasing absorption beyond 2.5 ohm. First reason is not a limiting factor of the system itself. The fiber absorption may be circumvented by employing, for example, a coupling prism or tapered chalcogenide fibers instead. So I have two different fibers being, I don't know how to spell. You guys have it F-I-B-R-E-S, and then other PDFs that have F-I-B-E-R-S. I'm confused. Pertaining to the advantages of crystalline microresonator based mid-infrared frequency comb generators, it is noted that the native mode spacing in the range of 10 to 110 GHz is one unique feature. On the one hand, the comb repetition rate and carry envelope offset frequencies are accessible with suitably fast photodetectors, electronics, and digital signal processing. On the other hand, the comb modes may be individually accessed and even controlled. Indeed, a growing number of emerging applications require combs with large line spacing, such as astronomical spectrograph calibration, arbitrary optical waveform synthesis, and spectroscopy. Line-by-line pulse shaping of individual comb lines may prove beneficial to coherent control of chemical reactions. Moreover, the ability to dispersively separate the individual modes of the mid-infrared Kerr comb with a single grating onto a detector array enables a direct fingerprinting of molecular absorption. In summary, a crystalline microresonator-based optical frequency comb in the mid-infrared molecular fingerprint region is demonstrated for the first time. Oh, cool. This is also the first time that a keracomb is generated in the strongly anomalous dispersion region, which was previously considered unfavorable for keracomb generation. The high power per comb line and the potential to extend the comb to longer wavelengths makes it a promising candidate for spectroscopic applications. Moreover, the combination of crystalline microresonators with mid-infrared QCLs, which can generate high CW power output power at room temperature, could open the path to novel, simple, and compact mid-infrared comb generators. Furthermore, the choice of the microresonator material is not limited to dielectric crystals, as many semiconductors such as silicon Si, germanium, Ge, indium phosphide, and IMP also exhibit wide transparency windows in the mid-infrared and third-order nonlinear. See methods in supplementary table S2. A whole class of on-chip microresonator frequency combs for molecular spectrometers based on this approach is conceivable. And it's www.nature.com is the link. And it's going to continue. Oh my god, this takes forever, right? Mid-infrared optical frequency combs at 2.5 ohm based on crystalline microresonators and material choice. That's going to be in our next video.